Hello class. Hey look.
Hey,
How are you?
I'm good. Hey Louis, guess what's in my hand?
Whoa. You must have a magnet in there because I know that's a magnet.
You're right.
Oh, nice little bar magnet. I have one too.
Oh, do you teach about magnets in your class?
We do. Well, permanent magnets are a little tricky, it turns out, actually. To explain where the magnetism comes from has to do with the spin of the particle. You even need quantum mechanics to really understand it. So,
Hold down there. Let's just talk about electromagnet.
yeah, we will talk about electromagnets though. Those are simpler. These are the ones where we create their magnets, kind of artificial. It's created by electric field and electric current. And, yeah. But what we need to know about bar magnets is they just create the magnetic field. And remember from when we did electricity, if we have a positive electric charge, it will create an electric field, which is radially outward, spherical, and this electric field is everywhere in space, and if you put another particle there, it will feel a force. Now we also seen that if you put a positive charge and a negative charge next to each other, then you get a different field pattern, and it's called a dipole in this case, and the field line, the electric field line, goes from the positive to the negative. What do you think this one looks like?
My back guys would be this one.
Yes, it should look like a magnetic dipole, right, essentially. So let's see, what I have here is a bunch of little pieces of irons that I can move, that essentially can move kind of in small circles, and I can use the magnet to move them. And if I put my magnet on top, these little pieces of iron will essentially align themselves along the magnetic field. So just by looking here, we see that pretty much looks like. So let me draw a bar magnet. Has a south and a north. This is usually how we denote the two hands. And the magnetic field lines, go from the north pole to the south pole. Okay? And this pattern looks like the electric dipole, and really kind of what it is. What do you think happens if I was to cut this magnet in two?
I think you will get two magnets.
That's right. Good. So let's try this here. I have two magnets, and so therefore two dipoles patterned. So let's try this again. Just half of the magnet now. And again, it looks the same kind of pattern. If I cut this, in half, I don't get a south pole and a north pole independently. I get still a full south and north. And then the magnetic field goes from north to south. Okay. It's actually extremely interesting that we've never found in nature a monopole, a pure charge of magnetism. Everything we see in nature, all the bar magnets, all the electromagnets that we can produce, are doing dipole. They're producing a magnetic field that goes from one end to the other. Now we can visualize this even better in 3D if instead of using a little plate like this, magnets are strong, bunch of little pieces of iron inside of a liquid, and I just put this here and use a magnet, maybe not as strong as these ones, like this one, and put it inside. We should be able to see a three-dimensional pattern of the magnetic field. Again, the little pieces of iron will align themselves around the magnetic field, so we can visualize the magnetic field of this magnet.